It's being called Y2K2. Hi, everybody. Karen Rovey here for ZDNet. Scott Fulton joining me here in just a minute to talk about this. You know, it's a time when it becomes possible for all encrypted communications everywhere to suddenly stop being a secret and be readable to everyone. But who has access to a quantum computer? That's a question here. We're going to hand it over to Scott to hopefully not confuse things on this subject even more. Scott?
You have access to a quantum computer. You can actually make a quantum program right now if you knew what you're doing, or even if you don't know what you're doing. There's experiments you can do. And we just published on ZDNet a quantum as a service buyer's guide, where I picked 5 services, including the venerable Amazon bracket, with which you could experiment on a free level with making a quantum program. If you ever had the inclination, and what could you possibly want to do with your own access to a quantum computer? That's something that's being discussed this week. As I speak right now, there is the virtual Inside Quantum Technology Conference. It's held twice a year, once based in Europe and once based in New York. The New York version is going on right now as we speak. And even if you're watching this after the conference is over, you'll probably be able to log on, register, and see the recorded conference sessions. And one of the big topics they're talking about is the one thing that some people may actually want to do with a quantum service, which is break all of human cryptography in recorded history up to now. This is the date that's being considered Y2K2, except we don't know what day it's going to be, day and date. We had the luxury of knowing that January 1st, 2000 was going to roll around. But we don't really know the date when it's going to be possible for a stable string of qubits to be leveraged to use a simple problem of factoring numbers, that finding the common factor in a big number that breaks all of public key infrastructure-based cryptography, the system through which emails are secured, and to some extent the system through which HTTPS protocol secures all the sessions on the World Wide Web. Now, could you conceivably want to do that with your rent-a-service Amazon bracket connection? Well, that's actually, I think it's a question for the service providers. If suddenly you've got a boon of users that are suddenly trying to break messages, I would think they might want to say, hey, that's not legal. You might want to stop that. But here's the problem. The theoretical capacity would exist for somebody with this type of direct access to a quantum computer that, guess what, we all now have, would be able to break a connection. What is the cryptographic connection? Well, the keys that you use in the cryptographic connections are based upon random numbers that are generated by multiplying together 2 very large prime numbers. One of those primes belongs to person A in the conversation, the other person to person B in the conversation. It's very easy for a calculator to take one key, which is one person's key to the conversation, and with that very large prime, divide the very large prime by the key and get the value for the other key. That's how we know we're talking to each other. We have access to each other's keys. But if all you have is the big prime number, the colossus, you don't know what the other 2 factors are. The act of factorization takes an extremely long time. Using a very fast supercomputer, a supercomputer scientist estimated that using something that you'd find on the top 500 computer, the top 500 computer list, it would take 111 years of 24/7 operation to find the right 2 factors. And by that time, 5G will be fast. In the meantime, it might take a quantum computer system, that thing that we all have access to now, about 6 minutes. So this this is a problem. If we expect our private intelligent communications systems to remain private and intelligent. So there's one of two or perhaps both solutions to this problem that are being worked on. One is a quantum computing solution, actually using quantum communications as a way of securing what we say to one another. And this is done by exploiting a factor of physics that photons, when exchanged like this, seem to know when they're being interfered with. So if you've got a private communication between two people and then something interferes with that communication, something or someone, they can't see anything. And of course, neither can anyone else, but at least it protects the communication. The other possibility is something called post-quantum cryptography, or PQC. And this is essentially the next order of algorithm that would replace PKI. It might still fundamentally be broken by quantum computing at some time, but maybe not in 6 minutes, and maybe in a period of time that would make it kind of impractical for anybody to want to do that. But these are the two solutions that folks are hoping will save us from the dreaded Y2K2.
Okay, Scott. So when you talk about the quantum safety, would that have helped defend, say, Colonial Pipeline? As we know, it's been in the news because of this recent ransomware attack that they experienced.
Well, I'm going to be controversial about that and say, no, it wouldn't solve the Colonial Pipeline dilemma. And I'll tell you why. There's two types of security we're talking about. There is communication security and there's system security. The Colonial Pipeline incident was an exploit of system security. It managed to get malware across the line one way or the other, and it could have done that through an email hack or an attachment to an email, or it might have done it by implanting a control in a website. And that's happened before. It implants a little Trojan and it gets into your system through a website that people normally use. This happens to me. It probably happens to you, but we have pretty good antivirus to keep ourselves from being exploited by the channel that opens up. And right now, I'm not exploitable because I have modern antivirus. And Colonial Pipeline probably didn't. And there was the difference. That was a system security issue, which brings up an awfully good point. If quantum communications manages to make the channels between point A and point B more secure, then you could still deliver ransomware over that communications channel. And that ransomware might be harder to track. So the security solution might become a security problem. And the National Security Agency has been looking into this very problem, and to what happens when it would be theoretically possible for something as ubiquitous as a WhatsApp to deliver you or anyone a $5 million ransom note. And this is one of the problems that's being discussed at the IQT conference this week. And we're going to be talking more about that in ZDNet as with coming issues.
All right, Scott, thank you so much for that. For much more on Scott's article, make sure you check it out on ZDNet. We appreciate you watching us here today.